Hello everyone. In this session we are going to focus on timer using C programming. Okay. We have worked on few problems in the earlier sessions and we used assembly at that time. So today in this session we are going to use C programming to demonstrate the working of the timers as well as to generate custom delays and custom frequencies. Okay. So let us now focus on the timer in modes, different modes. The timer in mode 0 can achieve a maximum delay. You can achieve a maximum delay of 8192 into 1.085 microseconds. So that comes to approximately 8.88 milliseconds. For timer in mode 1, so you can achieve a maximum delay of approximately 65,536 into 1.085 microseconds. That comes to 71.1 millisecond. And the timer in mode 2, you can achieve a delay of 256 into 1.085 microseconds. So that is equal to 277 microseconds approximately, or 0.277 milliseconds. Okay. Now let us go to Keil and let us start writing a C program for timer. Okay. So the C program starts with include reg 51.h. So this is the this is the header file that contains register definitions, and then void main void. Okay. It was always a good practice to open a flower bracket and close as soon as you have opened a flower bracket. So now inside this program, what we'll do is we will set tmod to 0x00. We'll use timer 0 in mode 0. So tmod is equal to 0x00. Then th0 is equal to 0x00. tl0 is equal to 0x00. Okay, and then I am going to complement pin port bit 5 of port 1. So p1 1 is equal to tilde p1. So what happens here is the entire port 1 will be complemented. Then I am going to run timer 0 by setting it to 1. Okay. Okay, so let us see what is happening in each of this line. The tmod is equal to 00 means the timer is in mode 0. Now we will be using timer 0. So when you set th0 is equal to 0x00 and tl0 is equal to 0x00, it has you can get a maximum possible delay in using timer in mode 0. Okay, that means the timer T0 will increment from 0000 till FF1F. Because why is it so? Because TH0 is in 8-bit mode and TL0 is in 5-bit mode. Okay, so then immediately we are complementing the port P1 and then we are running the timer. Now once the timer overflows, the TF0 will be 1. Till then TF0 will be 0. So we will loop using while statement, okay, as long as the TF0 is equal to 0. Once TF0 becomes 1, we will exit from the while loop and then we will reset TF0 as well as we will stop the timer. Okay, TR0 is equal to 0. Okay, and now these logics that are highlighted should be run in an infinite loop if we want to generate a square wave. So let me put the while statement here. While while true, then execute the logics. Okay, to run the timer, to set the timer, and to complement the port 1 to run the timer, and to check whether the timer has overflown or not. Okay, so this is the simplest program to generate a square wave with the timer in mode 0. Okay, Now having written this program, let us compile this particular program. Okay, so we have so many errors. Okay, TL0. Okay, so the reason is the spelling of include, INCLUDE. So that is the right word. Okay, let's compile it again. Okay, we have not got any error this time, 0 errors. Okay, so let us run the session in the debug mode, and let me see. Okay, logic analyzer is already up and running. So what we are going to do is we are going to run the program. So this is in mode 0. So the delay that I expect, maximum possible delay that I expect, is 8.88 milliseconds. Okay, so let me stop my program, zoom in. Okay, and let me stop my program and let me zoom in. Okay, and let me take some value. I'll treat different baseline now. I'll take the reference as 0.258619 second. I'll take a reference where the bit 5 of port 1 transition from low to high, that is 0.258619 second. Okay, let me write it down. 0.258619 second. Okay, and the transition from high to low happens at 0.267499 second. 0.264 267,499 second. Okay, so 0.267944 seconds, and let me confirm 0.267,499 second. Okay, 499 second, 499 second. Okay, so let me open my calculator and let me calculate what is the delay that I have achieved. 0.267,499 minus 0.258619. So this gives me a delay of 8.88 milliseconds. So this is in seconds, so the delay is 8.88 milliseconds, which is as expected. Okay, now let me run the program with the timer set in mode 1. So T mod is set to 1. Then there is no other changes in the program. So let me compile this particular program, and let me put the session in the debug mode. Okay, when the timer is set in mode 1, the maximum possible delay that can be achieved by the timer is 71.1 milliseconds. So let us run this and check in the logic analyzer. Okay, I'll stop the program. Okay, so I will take a reference when the transition happens from low to high. So when the transition happens from low to high, the reading that I have is 2.0633 seconds. 2.0633 seconds. So let me take that reading, 2.0633 seconds, and the transition happens from high to low at 2.1345 seconds. 2.1345 seconds. So the total delay offered is 2.1345 2.6345 minus 2.0633, so that is equal to 0.0712 seconds or 71.2 milliseconds. So I was expecting 71.1 milliseconds. So the delay offered here is approximately 71.2 milliseconds, so which is closely matching with the expected value. Okay, so let me go back to the Keil session and let me stop this program execution, and I'll set the timer in mode 2 and recompile the project. When the timer is in mode 2, the delay that I expect is approximately 278 microseconds or 0.278 milliseconds. So let me put the program in the debug session and let me run the program. Okay. Okay, I can see the square wave now. I'll randomly take one interval. Okay, I'll zoom out. Okay, I have to zoom in. Okay, so I'll take this particular state. I'll take the baseline as the transition from low to high, that is it's showing the reading of 2.410858 410,858. Okay, so that is when the transition happens from low to high. Now the transition happens from high to low at 2.4114. 2.41148 seconds. Okay, so the total delay offered by the timer in mode 2 is 2.41148 minus 2.410,858. So that gives us 0.00029 seconds or 0.29 milliseconds. I was expecting 0.278 milliseconds, so I got 0.29 milliseconds. The reason being is whenever the value of the timer becomes lesser and lesser, or the number of increments in the timer becomes lesser and lesser, at that time the delay introduced by the rest of the commands becomes significant. So that is the reason why you see the deviation of the observed results from the expected results. Okay, let us go to the next problem. This problem states that you need to generate a square wave at bit number 5 in port 1 with a frequency of 10 Hertz. Assume the clock frequency of 11.0592 megahertz. Now the time period for 10 Hertz corresponds to 100 milliseconds. So P1.5 should be high for 50 milliseconds and low for another 50 milliseconds. Now is this achievable? Yes, this can be achievable in mode 1 because the maximum possible delay in mode 1 is 71.1 milliseconds. Okay, so let us see what is the value of the counter that needs to be set, the timer that needs to be set in T0. So to achieve a delay of 50 milliseconds, so each of the increment in timer will take 1.085 microseconds, that is a machine cycle. So to achieve a delay of 50 milliseconds, the timer has to increment by a factor of 46,083. Okay, so that corresponds to B403. Now, if this is the number of count that the timer has to increment, then we have to work backward from FFFF to these many number of counts to achieve the value of the timer. So, computing that, the timer value will be FFFF minus B403 plus 1. So, that gives us a value of 4BFD. So, TH0 should be loaded with 4B and TL0 should be loaded with FD. So, let us go back to the Keil and set these value for the timer. So coming back, 4B and FD. Okay. TH0 is 4B and TL0 is FD. Okay, and the timer is in mode 1. Okay. So let us compile this project. Okay, and let us debug this and run this program. Okay, so let me stop the program. Okay, so if the frequency is 10 Hertz, then the time period should be equal to 0.1. Okay, so let us see the time it takes for for the entire time period. So let us see what is the at what time the transition happens from 0 to 1. It is 1.8512 seconds, and it goes to 0 to 1 again at 1.9512 seconds. So 1.9512 minus 1.8512, that is approximately 0.1 seconds. So this square wave is having a time period of 0.1 seconds, or the frequency of 10 Hertz. Okay, so let us go to the next problem. Okay, so the next problem states that generate a square wave with using timer in mode 1, and the square wave should be generated in bit 5 of port 1, and the frequency of oscillation should be 0.1 Hertz. Okay, so if the frequency of oscillation is 0.1 Hertz, then the time period is 10 seconds. So P1.5 should be high for 5 seconds and low for another 5 seconds. So is this achievable? Is the delay of 5 seconds achievable in using timer in mode 1? No, it is not achievable, because the maximum possible delay in provided by the timer in mode 1 is 71.1 millisecond. So 5 second delay can be split into 100 iteration of 50 milliseconds delay. Okay, so I will iterate my program 100 times, and that particular program provides a delay of 50 milliseconds. Now this can be achievable. Okay, so from the previous program we calculated that for a 50 millisecond delay, the value of TH0 and TL0 is 4BFT. Okay, so let us go to the Keil session and modify this particular program to provide it time to generate a square wave with the time period of 10 seconds. Okay, so now let us see. What I'm going to do is I'm going to take this toggling of port 1 out of the while loop, and the while loop simply generates a delay. Okay, I'm going to, okay, not here, I'm going to put it as a first statement within a while loop, and then I am going to regroup this program. Now if I see this set of instructions, this set of instructions provides a delay of 50 milliseconds. Now I'm going to define a unsigned integer, SIGNED count. Okay, and I'm going to iterate the count 100 times. Okay, for I count count is equal to 0, count less than 100, count plus plus, open the flower bracket and close the flower bracket here. Okay, let us see what this program does now. If you see, this instruction provide a delay of 50 milliseconds. Now this is executed 100 times, so this instructions that are highlighted provide a delay of 100 into 50 millisecond delay. Okay, and once the delay is provided, that is 100 into 50 milliseconds, that is 5 seconds, then it exits, then it will toggle port 1, and this particular logic will be executed infinite number of times. So let us compile this program. Okay, there are no errors, and let me put the session in the debug mode. Okay, and let me execute the program. Okay, and okay, as per the calculation, so what I expect is the transition to happen at approximately 5th second. So this is where the transition should happen. Okay, yeah, it has happened from 0 to 1, and the second transition from high to low should happen approximately at 10th second. So let me go to the 10th second. Okay, so this is where you can see that it's a 10th second. Okay, yeah, it has happened. The transition from high to low has happened at the 10th second. So if I consider the entire period, it is 10 seconds. Okay, so I can further proceed. At the 15th second, it's going to change from low to high. Yeah, it has changed from low to high. Okay, so that is about the C programming, generating a particular frequency of waveform